Thank you all for coming to the 25th annual Thomas Hayden Show. We're going to get started with all the fun chemistry demonstrations that you are all waiting for. Before we begin, we have the honor of having the president of Queens College here just to give you a few words. So please welcome President Frank Wu.
All right, good morning. We're going to blow some stuff up. I always make it a point to come out to see this show. It is just fantastic. So my name is Frank Wu. I'm the president here at Queens College on our beautiful campus right in the heart of Flushing. I want to thank everyone who's a part of entertaining and educating you, and our Associate Provost, Natalia Holtzman, who oversees all of this in this wonderful program. So I'm here to welcome you and to tell you that since it's January, it's once again time for the Chemistry Lecture Demonstration Show, which honors one of our former colleagues, Thomas J. Hayden. He was the director of the laboratories here at Queens College and helped with chemistry and biochemistry. He was the chief college laboratory tech for 40 years. That's 2 generations. He loved to use his extensive expertise and knowledge to present just the sort of show that you're going to see this morning. This type of demonstration that draws people in to chemistry and the sciences in general. It's not just entertainment, though. We want you to know that chemistry, like all the sciences, like everything taught here at Queens College, will provide you with opportunity. It will open doors to countless different careers. And chemistry embodies the full spectrum of modern industries and tech. You know, if you have a smartphone on you, we all carry one of those everywhere, you know, it wouldn't be possible without chemistry. Of the 84 stable, non-radioactive elements found on the periodic table, at least 70 of them are present in every smartphone. And it wouldn't work without all of those elements, rare earth elements, and so much more. So the vivid colors that you see on your screen every time you're surfing the web, that comes from these chemicals, the rare earth metals in particular. And every time your phone vibrates, that's being caused by neodymium and dysprosium. I'm not even sure I'm pronouncing those correctly, but those are important elements that are present right there in your pocket. These amazing devices wouldn't be possible without chemistry and chemists. So we want to offer you this opportunity, this insight, not just today, but we hope that you'll consider coming here for 4 years to earn your undergraduate degree, or starting at one of our sister institutions, Queensboro or LaGuardia, and then transferring here, like almost half of our students do, because there are so many areas that are connected to chemistry. Forensics, oceanography, toxicology, quality assurance and control, health and safety, even dentistry, just to name a few. So if you choose to study chemistry, you also might become a talented chemistry teacher, like those who have brought you to our beautiful campus. And this fascination all starts, as Thomas Hayden knew, with taking a look at what chemistry can do. These explosions are so much more. They should entice you. You should be curious to find out what caused that bang that we're going to hear. So I know that if he were able to, he would tell you that this career in chemistry or biochemistry, or any of the sciences for that matter, is a great career. And this is a great place to start, right here at Queens College. So we want to challenge you, we want to entertain you, we want to educate you. I want to say welcome, Happy New Year. It's great to see you, as it always is. We hope that you'll be back here when you start your undergraduate career. So, on with the show. Thanks so much.
Okay, thank you, President Wu. So I know we all want to get started, but I'd be remiss to not talk about the history of this show. The very first show was just 2 years before we launched our first satellite, so it's been going on since the 50s. As President Wu had stated, we had Dr. Hayden here working as a teacher, as a colleague, and he started the show. It's named after him, and you are sitting in the lecture hall that has been given his name as well. But we need to have new generations of people continuing the show. For years, we had Dr. Streckis and Dr. Gaffney, who are actually here with us today to see the show in its newest iteration. Thank you all for coming. And Dr. Gopal Subramaniam has also been keeping this going and keeping it exciting with all of our former chemistry students, our chemistry professors, everyone here to show you the 25th anniversary of this version of the show. So here's everybody that's involved. I hope you enjoy everything. You're ready for the loud bangs. If you want any further information, you have an email up there. But I also must say that all of these demonstrations, or at least most of them, are dangerous. So please be cautious not to do these without parental or teacher supervision. Maybe you can't even do this in your high schools, but enjoy them today. Thank you.
Okay. Hello, everybody. So I know we have one birthday in the crowd today. Is there any other birthdays? Any other birthdays in January, even? It's just Katie's birthday? Oh, and Liam. Yes, and Liam's birthday. And we got someone back there. All right, so let's sing happy birthday to all those people. I already lit the birthday candle. All right, ready? Happy birthday to you. Happy birthday to you. Happy birthday, dear January babies. Happy birthday to you. Wait, it didn't work. Oh, there you go. Woo! All right. I was gonna say it didn't work. You don't get to have a birthday, but. All right. So this next one that I have here, right, that was for the January birthdays. Now I'm gonna do one for Valentine's Day. So I like to call this one the hunk of burning love. So I have some magnesium here, and I have some dry ice. What's dry ice made of? No. Carbon dioxide, not ice. So dry ice is made of carbon dioxide. Does anyone know what is in a fire extinguisher? Also carbon dioxide. So what I'm going to do, is I'm going to take this magnesium and I'm going to light it on fire. All right? So the reason I call this the hunk of burning love, right? So this should extinguish the fire, right? But no, their love for each other is so strong that they could burn through even a fire extinguisher. Happy Valentine's Day, everybody.
Fire in a cave. Fire in a cave.
Woo. Is it not enough? Still me?
Hello, ladies and gentlemen. Hello, ladies and gentlemen. Oh, how's your day been? That's good. My name's Joel Heitman. I teach chemistry, physics at Townsend Harris High School. And today we're going to do a little bit of chemistry, so that's all good. So right here I have a balloon. This balloon has a gas in it. How many have ever heard of a dirigible? Yeah, I know, it's old school. How about a blimp? How many have ever heard of the Hindenburg? Yeah? You've heard of the Hindenburg? Yeah. What's wrong with the Hindenburg? It blew up. That's right, it blew up because it was filled with hydrogen, just like this. Hydrogen's really cool because it has a great reactivity to it and allows us to do some interesting things. But, you know, better than that, we could just like float in the air with it if we didn't blow ourselves up. So it's all good. Here, let me help you with that. I don't know why, though. This does not seem like a very good idea. There you go. That's good enough. Okay. Did you guys sign the insurance waiver? All right, good. You're over the age of 18. It's all good. You guys really think this is a good idea? All right, let's get a vote. Who says we should do it? Whoa, 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 that's every hand. Oh my gosh. Oh my gosh. Mommy. Wait a minute, were those two balloons the same? Yeah, one was bigger than the other, right? What was different about those two balloons? Fire. I like fire. What's up, fire? So one, they both had fire? One had fire. The other one did not have fire. But you did feel or hear an explosion. All right, so let's talk about it for a second. The first balloon had hydrogen in it. Hydrogen, less dense than air, but explosive. Second balloon, helium, still less dense than air. But the reason why you still heard a pop or a bang was because the instantaneous release of those gases that were trapped inside the balloon had to rush out somewhere. So they rushed out very fast, and that's why we get what we call a shock wave, and that's what you heard. Ladies and gentlemen, helium and hydrogen, both less dense than air. One more fun than the other, I guess. Have a great day.
Okay, so today's been a pretty fun day, right? A little party time. We had pizza. So in the spirit of having a party, I want to make us some fun drinks, right? Let's see. I feel like water's pretty fun. It's really healthy, right? It's the new year. We're trying to stay hydrated, right? That's our goal for the new year. But, I mean, it is supposed to be a fun day, right? So what's a drink that we could make maybe that is a little bit more fun than water? Something kind of sweet, kind of tasty. Juice, fruit punch, I like that one. I got a little bit of a sweet tooth. So let's see if I can make some fruit punch for everybody. Ooh. Well, I'll make enough to share, let's say. Yeah, there we go. Actually, now that I'm looking at it, really should stick with my New Year's resolution. I think I should just stick with water. It's honestly healthier, right? And you guys should be more healthy too. If I'm gonna share, I'm just gonna give everybody water. All right. Ooh. Though, I feel like there's other drinks that they're still healthy, but they're not as like plain and boring as water. Milk, there we go, okay. Get our bones nice and strong, but still stay hydrated, all right. Okay. All right. So it's skim milk, right? Okay. Okay, so I got some milk for everybody. But actually, milk's kind of like boring. Is there any way we can make
Somebody in the
milk?
backside may not see that. All right. Milk for them too.
Is there any way we can make milk fun, though? Chocolate milk. Okay, let's see. Ooh. Kind of looks like Yoo-hoo, right? Kind of, a little bit. All right. And, all right. Water. So I got milk, I got chocolate milk, and let's see if I can turn this back into chocolate milk. And just in case anyone is being really strict with their New Year's resolution, I can turn it back into water also. All right, there we go. Well, it's like chunky water, but you should never drink anything in the chemistry lab anyway. All right, there we go.
Oh, hello. Okay. So we saw from the balloon that hydrogen is very reactive. So we're going to test if hydrogen in dish soap is more reactive, or if hydrogen in a ratio with oxygen, a 2-to-1 ratio with oxygen, is more reactive. Here is just the hydrogen and dish soap. Let's see. Oh, I didn't get any bubbles here.
Just make sure they open it up.
Okay. Oh.
There you go.
Yeah, this is bad, man. All right. Oh, did you hear that?
Not fun.
All right, now let's try hydrogen in a 2-to-1 ratio with oxygen. Oh, I didn't get any. Cover your ears. So, in the hydrogen only reacted with the oxygen on the surface, and in this one, it was mixed with oxygen to begin with, so it was more reactive. Thank you.
And welcome back. How's it going so far? All right, all right. So right here we have a compound called potassium chlorate. It's got some potassium in it. It's got some chlorine in it. But it's really the 8 we care about, because the 8, ATE, it means it's got a lot of oxygen in it. As a matter of fact, it's got 3 oxygens in it. And it's all trapped inside this solid compound that's white. But by heating that compound up, we can activate that oxygen, and we can use it to our advantage. Now, we can use that to our advantage 2 ways. One, well, we could just make a really big fire with it, which would be kind of cool. But the other way is we could take anything that has some type of sugar structure in it, and we can activate that sugar structure, and we can make some really neat things happen. So right here, I have a gummy bear. What's our gummy bear's name? Gerald. Hi, Gerald. Hi, everybody. I'm Gerald. Are you having fun today, Gerald? I'm having a blast today. Yeah, a blast. That's exactly what's going to happen in a second, a blast. All right. So here we go. We have our oxygen-rich atmosphere. Would you like to do the honors? All right. So just take that and pop it right in there real quick. Don't get it stuck on your gloves. And what's happening right now, that was a gummy bear. What is a gummy bear made up of? Sugar. And that's its prime ingredient. And that sugar is now being activated. And it's using that oxygen in there, and it's burning. And it's kind of neat and cool. What's this? It's what? What's wood made up of? Anybody know? Trees. Nice. You go to the front of the, oh, you are in the front of the class. I like it. All right. It has something in there called cellulose. And cellulose, ironically, also has sugar in it. And that's a pretty cool demo, the way I see it. Ladies and gentlemen, we call this the gummy bear sacrifice. And now it's my fireplace. Have a great day.
As a teacher, as a high school teacher, I don't make that much money, right? But I do like fancy things, right? I like to, maybe order on Uber Eats sometimes. Maybe I like to go on vacation. But as a teacher, I have to have a little side hustle. Thankfully, I'm a chemist, so I can actually make my own silver and gold. You guys want to see? All right, so here I have just a regular old penny, right? If anyone wants to confirm for me, I'll hand some out. Right? You guys agree? These are just regular old pennies, right? So what my lovely assistant here is going to do is he's going to take these and he's going to place a few into the magical solution. Where you're going to put them in. Yeah. Okay? And have you guys ever seen on cooking shows how they say, oh, you know, you're going to put it in the oven for 2 hours, but they magically have one prepared on the side? We're kind of doing the same thing. So I have my silver pennies now. Ooh, ah. And I will pass these around. And while I do that, my lovely assistant is going to place 2 onto the hot plate. So it's going to get nice and hot, and it's going to turn into gold. So would anyone like a silver penny? All right, you guys can pass that around. Okay, take home some riches from the Hayden show. Pass it around. All right, some silver for you guys, take home. And let's see how my gold is cooking. Can they see it up there?
That's the silver one.
Yeah.
Good one.
Oh, so there's my regular penny coming out of the solution. Got some silver going on there.
There is your silver, right out of there. Conversion. I don't want to give it to you, it's still filled with chemicals. Okay, go on with your gold.
Okay. All right, so on my hot plate, I have my silver pennies, and they're turning gold, but in the cooking show spirit, I have some prepared for you already, okay? Nice, shiny gold pennies. All right, and this is how I fund my lavish lifestyle.
Ladies and gentlemen, right here I have a crisp, clean dollar bill. I have my handy-dandy liquid. And I'm going to stick my dollar bill in the liquid. And I'm going to perform a magic trick in front of you all. I'm going to take that dollar bill. I'm going to wiggle it around a couple of times. I'm going to take that dollar bill out. And I'm going to ask my handy-dandy assistant to light my dollar bill on fire. Because I'm made of money, ladies and gentlemen. And I can spend it all day long. And I can still spend it. Dollar bill. Kind of cool.
$100 bill, want to give it?
Who has some money in here they'd like to see burnt? Oh, you got some money, huh? How much you got? You got a 50? No, I need something bigger than that. I need something bigger than a 20. I need something bigger than a 20. Yeah, I want big money. You got big money, don't you? That's right, we talking Benjamins, folks.
Do we trust him? Do we trust him with this?
Benjamins.
No? Huh?
Just give me the
I'm
money. Show me the money. There we go. Thanks a lot, everybody. Have a great day. Oh, chemistry. All right, let's take that Benjamin. Wait, would you like to on this and take on? Make sure it's real.
You don't trust me?
No way. It's good. We're going to take that real $100 bill. We're going to stick it in the liquid of fun. Just so you know that I didn't do anything funny. It was not funny money laying over there. All right, here we go. We take our funny money and we stick it in, our real $100 bill. We stick it in there and we light it. And there it goes. $100 bill on fire, just the way it goes when you go to the store. It burns right out of your pocket. Ladies and gentlemen, it's still a $100 bill. Thank you very much, Dr. Alafalo. But let me just help you out with one thing. Let's talk about what really happened here. Both of those pieces, currencies, were real. The dollar bill that I had and his $100 bill that, well, I want now. And what makes it really special is that it's a special combination of liquids, isopropyl alcohol and water. I'm not going to tell you the ratio because I don't want you to do it at home, because I don't want you to burn your money because you do it wrong. But what really is interesting is money is not all paper. It actually has cotton fibers in it. And it's that cotton fiber that absorbs the original water that's in there before the isopropyl alcohol, and the alcohol stays on the surface of the paper money, the cotton money. And then when we light it on fire, this does not happen. This is when you don't have water in there, and it's just alcohol. But that's why it doesn't burn, only the surface. And that's the alcohol that burns. And thanks a lot. Appreciate it. You remind me of my failed experiments. Ladies and gentlemen, money on fire. Have a great day.
75 cents.
No, still $1.
Okay. So I am a graduate of Queens College. As my kids know, I went to art school and I dropped out, and I came here to become a chemistry teacher. But I didn't actually choose to become a chemistry teacher. It was predicted. It came to me. So you guys know Harry Potter, like the Sorting Hat, right? It tells you what Harry Potter house you're going to be in. We have that at Queens College, but it's actually a glass, and we use some chemistry. So, I already did. Here they give you a cup and pour in some liquids, and the color that it changes tells you what you should be when you grow up. So if it turns yellow, you're going to be an artist. If it turns green, you're going to be a biologist. If it turns red, you're going to be a firefighter. And when my cup was poured, it turned blue. And that is how I became a chemistry teacher, right? The universe made that happen. So does anyone want to find out what they should be when they grow up? I need a volunteer. I'm gonna take that girl because she's using both hands. Come on down, girl. You take one, I'll take one. All right, so you are going to stand right in the middle. What's your name?
Jenna.
Jenna, all right, Jenna. So let's see what Jenna is going to be when she grows up. So we got two solutions here. We're going to pour both of them in. All right, are you ready? Yeah. You ready to find out your destiny? All right, let's go. Oh. Jenna is going to be nothing. Oh, wait. It's turning blue. She's going to be a chemistry teacher. Congratulations, Jenna.
Thank you.
All right, so this reaction is called iodine clock. I was just joking when I told her she was going to be nothing because it is a time-delayed reaction. I knew it was going to happen. Jenna, thank you.
Okay, good afternoon, everyone. My name is Olga Benyaminov, and I am a professor here. So today, I want to show you an experiment that would resemble what fireflies show. What do you see on a firefly? Light. So we're going to try and do that. This is called chemioluminescence. We're going to mix this special chemical, which is hydrogen peroxide. Mix it with a little bit of luminol. Luminol is this chemical that has a chemical reaction that allows this lightning to happen. Okay, ready? Awesome. Now
Hey, ladies and gentlemen, how we doing? I'm back again. I have this thing right here. It's called calcium chloride. That's a salt. I have this right here. It's called copper chloride. It's a salt. I have this right here. It's called lithium chloride. It's a salt. I have this next one here. It's called sodium. It's a salt. Yeah, you're getting the hang of it. But only the 4 in the front. The rest of you are like, what? All right. All right. Barium. And it's a. There we go. And then I have strontium. And it's a. There we go. All right. And I take all those salts and I put them in my nice dishes right there. And now I'm going to add something to it called methanol. Methanol is, well, no. Not even a little bit. It is flammable. that is what we talk about methanol for. And we're going to use that methanol to give it some activation energy because we want to excite these electrons because that's what we're looking for. Is we're looking for the excited state of these electrons. And as they excite themselves, we should see something happen when they come down in their energy levels. So you should pay attention to all these things that you see in front of you. I'm going to skip that. And we're going to see all those things that are in front of you. And let's turn some lights off and let's get a, I never know which button it is. There we go. Pretty. There we go. You may have seen something like this once in your lifetime above your heads. They call it, that's correct. They call it fireworks, and this is exactly how we make fireworks. We make fireworks by taking the salts, we put them in the firework, and then we ignite them. And then when they explode in the sky, the electron's excited, and when it comes down from the excited state, we see pretty colors. And a chemist once told me he was the most boring person to ever go to a fireworks show because he would stand there and go, oh, look, strontium chloride go across the sky. Everybody else is going, wow, look at that bang. All right. So, ladies and gentlemen, that is what we call the fireworks series, or the rainbow colors. So that's very nice. No, I don't want to try that. You make fireworks, well, you use something that gives you some activation energy, and you put a salt inside of it, and then, well, you launch it to space. So we're going to see how it launches. Here he goes. Only you. Had to be you. All right, count it down, Victoria.
I'll do it for you guys tomorrow at school.
What color was that?
Ladies and gentlemen, welcome again. So, are you guys having fun? You like what you see? All right. So, I have 3 metals here. I have sodium, magnesium, and potassium. Those are metals, right? What happens when you put a metal in water? Nothing. All right, end of the class for you. Stay for extra help. It rusts, right? Right. And so metals have these interesting properties that we like to talk about. And the first one we're going to look at is we're going to look at sodium, because sodium is pretty cool. We're going to grab our little tongs out here, and we're going to take a little piece of sodium. If I could grab a piece of sodium, it'd be nice. All right. I will get it out of there. There we go. Or not. It doesn't want to come out. That's okay. We'll win in the end. So here's my sodium right here on my counter. Now, you know metals to be nice and hard, but I could take my knife and I can cut that metal just like that. And so, and if we look inside of it, It will have a property. What are metals when we look at them? What do we see? Shiny. Well, does this look shiny to you? A little bit shiny, right? So we're going to take that metal and we're going to put it inside our little beaker here. I need some cloth, wire gauze. Anything other than this will make me happy. Perfect. There we go. Thank you very much. So we're going to take our sodium. That's a lot of sodium. And we're going to put it inside of our beaker. And we're going to look for a reaction to happen. I've never seen metal do that myself in water, but apparently it's having fun. No need to put that in there. Oh, and then it lights up. All right. So there's a reaction that occurs between the sodium and the water. It produces two products. It produces hydrogen gas, and it also produces hydroxide, which is a base, which is kind of neat. But that was sodium. Let's take a look at magnesium, folks. Now, let's take a look at the periodic table. We just looked at where the sodium was. Now, let's look at where the magnesium is. We'll take about the same amount of magnesium, and we're going to take that magnesium, and we're going to stick it in about the same amount of water. All right, we're going to use this one. We're going to flip these up here. And I would like you to pay attention to what you witness happen next. All for effect. Keep staring into oblivion. You might see some bubbles occur, so we could say that this would be more than this. What would we say that would be? I heard it out there. Speak loud and proud. That's right. It's more reactive. You got it. So let's take a look at potassium. Where's potassium on our periodic table? It's K, not P, just so you know. Some people forget that. All right. Yes, P is phosphorus. I agree with you. But K is potassium. And that's what we have right here. We have an equal size potassium to our sodium. There we go. Nice little piece of potassium right there. I'm going to put that up there. I don't want that one right there. And now we're going to do the same thing that we did with the sodium, with the potassium. Make sure your life insurance policies are in check. Wait for it. It's not done yet. How would we rate the potassium to the magnesium? Less or more? How would we rate the potassium to the sodium? Really? Did the sodium catch fire immediately? Did the potassium? Yes. Which was more reactive? We call this the reactivity series. As we go down the periodic table in that group 1, we'll see that things get more reactive. Ladies and gentlemen, the reactivity series of metals.
Okay, so we saw that metals produce a base, and now we're going to test how base can be changed to an acid. We'll start, not to an acid, I'm sorry, neutralized by an acid. So we're going to start with ammonium hydroxide, which is a base, and I'm going to add about 40 milliliters of that. And then we'll use an indicator. Where is my indicator? We'll use a universal indicator, which actually changes colors based on what it is. Acid has a different color than a base, so we'll start with a little bit of the indicator. Let's mix it, give it a shake. And then I'm going to add dry ice. So dry ice is carbon dioxide. When it reacts with water, it changes to carbonic acid. So actually water and just carbon dioxide is your club soda. When I put that to react, let me just add a little bit more. It neutralizes the base.
Hi.
More. Okay? It's happening. You see how it's changing to green? Slowly. And we'll accelerate it. We'll make it even faster. Come on. There you go. Or not. But then we can change it back using some more ammonia. And change it back using some more acid. And there you have it, a rainbow of colors.
Ladies and gentlemen, I am back again. Little background story. I am a graduate of Queens College, just like Victoria is or was. I graduated a long time ago. I now teach in the city, just like Victoria does. It's kind of nice. And but part of the reason why we have this show is so that we can actually teach aspiring teachers about doing some of these demos in the classroom, because it takes practice to do these. And so we have a class here at Queens College that helps teach teachers these demos and help get them more comfortable. Faith, I need an assistant. Faith is a upcoming teacher here from Queens College. She's a chemistry student. Faith, I would like you to describe all the properties of everything that you see right here for our audience. Go ahead, go.
So we have a rubber hose. It is bendable. It goes around.
Rubber hose.
We have a old banana. It is squishy and brown and kind of gross. We have a rubber ball that bounces. I'm not very good at catching it, but it bounces and it's squishy. And we have some beautiful flowers that you might get for Valentine's Day.
Hey, there you go.
So we're going to take the flowers, we're going to dump them.
We have some more nice ones. Yeah, you can give it to anybody whom you want.
Take them out. You can crumble.
See, I do this side, nothing happens. I do that side, they crumble. But is it still a flower? It is. What's inside our balloon over here? No. Helium, it would be doing what? Is it floating? Does it have helium in it? What's inside of it? Oxygen, yes, but more than that, it's that thing we breathe. Yes, air. We breathe that air, and that air is inside there. But if we're really careful and we take this and we pour the liquid nitrogen, which is minus 118 degrees Celsius, and we pour it over the top of this, and we keep pouring it on there, what's happening to all of those little gas molecules that are inside our balloon? They're evaporating, right? No! They're getting closer and closer together. And as they get closer and closer together, well, the volume kind of changes because the volume of the balloon isn't needed. Is it still a balloon, though, is I guess the big question. Well, let's take that balloon and let's put it on the counter and let's see what happens while it does that. Meanwhile, while that's doing its thing over there, here's our first thing out of our concoction. We call this the racquetball. Doesn't sound like a racquetball anymore, but is it a racquetball? Amazing what happens with that. Hold on, what else do we have in here? Oh wait, here's our rubber hose. Here's our rubber hose. Not very flexible. There goes our, oh wait, there's one more thing in here. The banana. It likes it swimming. It wants to swim. There we go, a banana. It's a very hard banana. But even though it's a hard banana, oh look, a nail and a banana. I can hammer a nail in a piece of wood with a banana. Pretty cool. But wait, there's more. You said it's not a balloon anymore. Looks like a balloon to me. Ladies and gentlemen, liquid nitrogen, volume of air, and changing physical properties. Excuse me, physical states. I said properties? I said properties? I just said properties. Hey everybody, guess what? I'm back. What do I have here? I have a glass wall. Why? Because you have to be protected. Why do you need protection? Because I have something in here called thermite. What is thermite? Some of you have heard of thermite because you watch those shows on YouTube that like to have thermite. Thermite is a mixture of aluminum and, okay, I want to just let it down. Iron. This is my little igniter. That's not the thermite. That's just my igniter. What will happen in about another 3 seconds is the thermite will now come out the bottom, and that's my thermite. Thermite creates a nice little thing called steel. Where are my tongs again? They're killing me. With the thermite, I can reach in here and I can grab the molten steel. Kind of neat, right? And well, wait, there's more. Once you start a thermite reaction, it doesn't stop, so it has to go to completion, and it burns at 3,600 degrees Celsius, and it's enough energy, if strapped to a rocket like the space shuttle, to help it go to space. Yes, those solid rocket boosters had thermite in them. Ladies and gentlemen, have a great day.
Hi, everyone. Is there a Hulk out there can crush this can for us? I doubt. Let the ethanol do the job for us, okay? We're gonna add a small amount of ethanol. You can do it for us. We're gonna add the ethanol inside the bottle. We're gonna rotate it to coat the inner surface of the inner.
So make sure that all the liquid can cover the whole can.
And we want to produce some ethanol vapor. Today we're gonna discover the interplay between the combustion reactions and the air pressure. We're gonna remove the extra to make it safe for us and you. Okay. Let's see the wonder of chemical reactions.
So let's take let's see how the can goes.
As you can see, the combustion, we're able to crush this can.
Okay, thank you guys.
Thank you so much.
Okay, so here is a story about Giggles, the elephant from Bronx Zoo. What do elephants eat? Ideally, peanuts. But our elephant actually loves candies. So what happens when you eat a lot of candies? You get cavities. So we want to help the elephant prevent that. We're going to make some toothpaste. We'll start with hydrogen peroxide. And what does hydrogen peroxide do to your teeth? Whitening. Then we're going to need to take all that junk out with some soap, some food coloring for the stripes of the toothpaste, if I can get some. Bear with me. It's happening. But this reaction actually would take so long if I don't help it. going to take a few months to actually generate that soap. So I'm going to have an accelerating, a catalyst, potassium iodide, added to the mixture. Woo! Did not expect that. Here you go. That was fast.
Okay, so I don't know what it's like at your school, but I know at our school we are not even allowed to have the gas turned on, right? So you guys in chemistry lab and STEM room, you like to play with the little knobs and you hear that, and you're like, Miss, is the building gonna blow up? No, we don't even have gas at our school. But I have gas here, and I'm gonna show you guys why they don't let me play with fire at school. All right. Okay, so this gas is flammable, and I'm gonna make some bubbles. If I'm strong enough to move it. Yeah, there we go. All right. So, what do you think would happen if I tried to light these bubbles on fire? All right, let's see. We'll do a little experiment. I want lots and lots and lots of bubbles. Huh? I'll just stand on both sides. Here. Hmm? All right, I think that's enough bubbles. So let's see. All right, are we ready? I like it.
Hello! I'm back! Well, I'm old. Oh, wait. I need these glasses right here. These are my safety goggles. Dun, dun, dun. Ladies and gentlemen, we have something out in the world called sodium polyacrylate. And sodium polyacrylate's really cool because, well, it's the things that diapers are made of. Everybody had a diaper in their life once. So we can take our super absorbency sodium polyacrylate laden diaper, we can fill it up with a lot of that stuff. You know what it's called. That's not water when it comes out of you. That's right. We're filling our diaper up. Faith, can you give me a hand, please, Faith? Faith, hold both sides of this diaper for me. There we go. Open it up really big and wide. Yep, as we pour it all in there. And we see that none of that water is going anywhere except, well, into the diaper, ladies and gentlemen. Thank you very much, Faith. We're not done yet. So we wiggle it around a little bit, and we see that the water is, well, absorbed. It's absorbed.
This child is leaking.
That's not bad. That's a lot of water we put in there, right? We use polar diaper. Okay, well, let's see how much we really put in there, though. That's really the fun part about it. So we see that we took about a capful, and we put it in there like so. And then we take the same amount of water, and we fill up our for effect. I want to make sure we get it all in there. And we pour it into our sodium polyacrylate, which is super absorbency. And we see that that much water went into that much sodium polyacrylate. And just to test how well it works, ladies and gentlemen, this is Dr. Galafalo. He was one of my professors when I was a student here at Queens College. He gave me a really, really awesome grade. And I think everything should go back where it belongs. That's how absorbency it is. Sodium polyacrylate, ladies and gentlemen. That's not mine.
Okay. All right. So the cool thing about chemistry is you can use things for multiple different things. So we have the sodium polyacrylate that was in the diaper. And did you know that the same thing is used to make fake snow in the movies? This house is... Okay, so I'm going to add... That's right, Jaden. Yeah, we were supposed to have a snowstorm last weekend, and I was so excited to be, like, snowed in and, you know, looking at all the pretty snow, and then it just turned out to kind of be like a wet mess. So thankfully I'm a chemist, and I can make my own snow. Right, so happy holidays, everybody. It is, right? Okay. Ah, yes, I need my umbrella because the weather's about to get a little bit weather. All right. So thankfully I brought my umbrella. I don't know, when you go out in the snow, like it's kind of cute, right? It gets caught in your hair and it's like la 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 la. When it's raining, however, it's kind of gross, right? So I brought my umbrella. And you guys have the internet, right? So in front of me, I have some soda, and I have some Mentos. All right, you know what it is? Okay. All right, are we ready for it to get wet and sticky in here? Give me a countdown. 5.
Ladies and gentlemen, unfortunately, like all things, shows must come to an end today. But we want to leave you with some more excitement before we leave. We call this the Fat Man. We have another one around here. We call that Little Big Boy. We're going to start with Fat Man. Fat Man has something in it called calcium carbide. Calcium carbide is made up of lime and calcium, and we mix it and it creates acetylene, and when we light it, well, it becomes like a really big cannon. So, well, here we go. A really big cannon. Tara, I think it's your turn. Fill it with water. Squeeze a good amount. That's good. Shake it up. You know you're gonna light it.
What?
You're gonna light it. Look. Other side. Ladies and gentlemen, thank you for coming today. I hope you enjoyed the show.
Thank you, everyone. Okay, I want to thank all of our presenters and thank all of you for coming to our show today. A lot of work went into it, so we all hope that you had a lot of fun. And as I mentioned before, feel free to visit our website. There's some contact information if you want to take a picture of that. And we hope to see you soon back here at Queens College. Thank you, everyone.